Here we're going to talk about phase changes. So liquid vapor phase transitions, solid liquid phase transitions, and then also solid vapor phase transitions. So first, a phase. Phase is a homogeneous part of a system that's separated from the rest of a system by a well-defined boundary. So classic example would be solid, liquid, gas. So there would be a clear distinction between a solid phase and a liquid phase, for example. There would be a well-defined boundary. And of course, we can go through a phase change. So we can change from one phase to another. So that's when any particular substance goes from one phase to any other phase. In general, we're probably pretty familiar with this just in terms of something like water, but generally this is the addition or removal of energy, usually in the form of heat, that can cause these phase transitions. And again, just with water, we're very familiar with these phase transitions. So here are some examples. You can freeze water, so that's water going from liquid to water as a solid. Evaporation of water, which we also call vaporization, liquid to a gas. Melting of ice is solid to liquid. Fusion is the liquid to solid. Condensation of water vapor, gas to a liquid. And then there's also, you can even skip liquid instead of going from solid liquid to gas or from gas liquid to solid. You can do sublimation. So sublimation is dry ice, which is solid CO2, going to gaseous CO2. So you can skip the liquid phase, for example, and that's called sublimation. The opposite of sublimation is called deposition, where you're going straight from a solid, straight from a gas to a solid. So these are all these phase changes again, showing kind of pictorially what's going on. So solid liquid to a gas, you have melting, which is synonymous with fusion here, so on and so forth. All right, so some of these phase changes, we have points associated with them, like a boiling point. Again, we're probably very familiar with this. So this is the temperature at which vapor pressure equals the external atmospheric pressure. We can talk about a normal boiling point, and that's the temperature at which the vapor pressure of a liquid is equal to 1 atmosphere. So yeah, it's when that particular liquid is boiling. So we're familiar with this obviously in terms of water, water boiling at 100 degrees Celsius. So that would be the boiling point. And that would be when it equals 1 atmosphere, and that's the normal boiling point. The boiling point of water can change if you're at, for example, high elevation, where you have slightly different than 1 atmosphere. So maybe you're familiar with that. We also have something called molar heat of vaporization, so delta H vaporization, or VAP. This is the amount of heat required to vaporize 1 mole of a substance at its boiling point. So there's actually a certain amount of energy that's required to actually transition that material from a liquid to a gas. So even though its temperature wouldn't be rising during this, you need to give it a certain amount of energy still in order to transition that material, or whatever that is, a mole of that material, to a gas. These are quite related to boiling points, this molar heat of vaporization. So you can see the high boiling points, like even, let's say, the high boiling points have the high delta H of vaporization, and ethanol, sorry, it should be 78.3 degrees Celsius, I believe. So that's not 783 degrees Celsius. So you can see in general, as you're increasing the boiling point, the delta H, the molar heat of vaporization, also is increasing. And that's in kilojoules per mole. So per mole of substance, it takes a certain amount of kilojoules, a certain amount of energy to do that transition at its boiling point. We have a few other ideas here. So one is called the critical temperature. And this is interesting. It's the point in which the gas phase cannot be liquefied, no matter how great the applied pressure. You also have something called a critical pressure. This is the minimum pressure that must be applied to liquefy a substance at its critical temperature. And lastly, a supercritical fluid. It's a fluid at a temperature and pressure that exceeds both the critical pressure and critical temperature, respectively. And this is supercritical fluids are fairly strange and bizarre. It seems it's kind of like a mixture of it has some gaseous and some liquid properties associated with it. So these, if you come across these, that's what these are. I don't stress this too much. All right, so phase changes. Again, we've already talked about this, but transitions of liquid to a solid. This is also called freezing, right? Melting is the opposite of this, going from solid to a liquid. It's the reverse process of fusion. The melting point of a solid or the freezing point of a liquid is the temperature at which the solid and liquid phases coexist in equilibrium. And then you can have this normal melting or freezing point of a substance, and this is just when we're at 1 atmosphere. So this is the temperature in which it melts or freezes while at 1 atmosphere. And then lastly, there's this idea of supercooling. And it's this fairly strange phenomena in which you can actually have a liquid be temporarily cooled below its freezing point. And this maybe you've seen this before, but someone will put like a water bottle in the freezer for a certain amount of time. They pull it out, it's clear liquid, and then they'll shock it somehow, like hit it on a counter or start pouring it out, and it'll immediately freeze. That was a supercooling process where that liquid was temporarily below its freezing point, and it took something to initiate that phase transition, like some sort of shock. So yeah, if you've seen that, that's what's actually occurring there. All right, so we talked about delta H of vaporization. We also have a delta H of fusion, so that's a molar heat of fusion. This again is going to be expressed in kilojoules per mole, and this is exactly what you would probably expect it to be. It's the amount of energy required to melt 1 mole of a solid at its melting point. Okay, so here's again a kind of a table of these molar heats of fusions, and again you'd expect it somewhat to be related to its melting point, and indeed that's mostly true. So there you have it. And yeah, these are some of the strange ones, the sublimation and deposition, for example. So here, sublimation, process by which molecules go directly to the solid from the solid phase to the vapor phase. So a solid that you see kind of smoking, for example, that is a sublimation process. And then deposition, that's when these molecules go directly from a vapor phase to a solid phase, and it's the reverse process. So here you can actually see a deposition that's occurring. So you have something that is oftentimes what you'll see is that something will be heated up here, so for example, and then it'll get into a vapor phase, and then you can deposit it on something that's quite cold. So here's ice chunks in here, and so you see we're getting these crystals growing on the bottom. That is a deposition process where there is some vapor in here that's being deposited on the cold surface. It's a way to do a purification for particular compounds and particular so that's what is likely occurring there. So just like we had delta H's for these other processes, we can have a molar enthalpy of sublimation, delta H sublimation. Again, this is usually expressed in kilojoules instead of, it should often be expressed in kilojoules per mole. Sometimes it'll just be in kilojoules. But it is expressed in kilojoules required to sublime 1 mole of a solid. And it's just the summation of delta H fusion and delta H vaporization. Because you're going through both processes energetically, so to speak, even if you're not explicitly going through both of those. So it's just the summation of those two. So we never actually have to look up delta H sublimation if we have the heat of fusion, heat of vaporization. So this is a phase change associated with temperature and the heat added. it is very important to note that this is all at 1 atmosphere. If you change the pressure, this whole system will change a little bit. So you have to be careful. This is all at 1 atmosphere. So here, as we add heat, which is the bottom, along the bottom here, we're adding heat. Let's say I'm starting with ice at negative 25 degrees Celsius. I start adding heat and it makes sense, its temperature rises. But once it hits 0 degrees, its temperature stops rising. Its ice went right here, and then we undergo a phase transition. That phase transition is transitioning ice melting into the liquid, into liquid water. That takes a certain amount of energy, and in fact you can see here it takes 6.02 kilojoules per mole. This is the delta H of fusion. So this is the molar enthalpy of fusion, or sometimes called the heat of fusion. Okay, so that's the energy that's required here. And again, positive or negative depending on which way you're going. So just be careful about that, thinking about whether you're gaining energy or losing energy in that process. And then once I have liquid water at 0 degrees Celsius, I can continue adding energy to that, and as you add that heat energy, you end up increasing the temperature, which makes sense. We've all seen water warming up on a stove top, for example. But then we're going to hit its boiling point. Its boiling point's 100 degrees Celsius at 1 atmosphere. And then it's going to take a lot of energy to transition this water from 100 degrees Celsius water to 100 degrees Celsius water vapor to gas. And that takes a lot more energy. That's the vaporizing the liquid water to steam. So this is delta H vaporization, the standard the enthalpy of vaporization. So this is kind of interesting because there is a common misconception that, like, for example, that what this is saying is that water is never getting over 100 degrees Celsius, and that's true. So sometimes people will talk about, oh, if you boil something very like let's say very aggressively, it'll get too hot. Well, the water really can't get above 100 degrees Celsius. It'll turn into more water vapor, and that water vapor certainly can be a lot hotter. And this is why steam can burn so much easier in many respects than water. So steam can get a lot hotter than boiling water. And this will also change depending on the pressure. So if you decrease the pressure, like let's say you go up at very high elevations, let's say you're trying to boil water in something like Denver, you're going to have a slight decrease in boiling point. The boiling point might be 96 degrees. You have lower pressure at that elevation, so it's going to be easier for you to break these bonds and get the water into water vapor. And that's why quote unquote high elevation cooking takes a little bit longer, where if your water is only boiling at 96 degrees or something like that, you're at a slightly cooler temperature, so it's going to take a little bit longer to cook something, for example. This is also the idea behind pressure cookers. If a pressure cooker, if you can get up to a few atmospheres, that water, that liquid water, can actually be much higher in temperature because you have a much higher pressure. So you can, with a pressure cooker, you can cook something a lot faster, right? So these are the ideas behind that. But there's some common misconceptions. It does require energy to transition water into water vapor, and you're adding heat energy, though the temperature is not changing. That energy is going into breaking those intermolecular forces in the liquid and getting them into the gas form. Okay, so actually it has a lot of implications associated with this particular idea, and as we'll find, means when we do problems, sometimes we're going to be starting in the middle of some phase. We're going to be going to the end of another phase. So for example, if I'm trying to figure out how much energy it takes to boil water, transition water at 50 degrees Celsius into steam, I need to account for the transition of 50 degrees Celsius water up to 100 degrees Celsius water. Remember, this was Q equals MC delta T, where you had the specific heat of water, you have a certain mass associated with water, and a change in temperature associated with water. So we know how to calculate the change in temperature of a particular substance if we know its specific heat, which of course for water we do. But then we're going to need to deal with the delta H vaporization, or if we're doing a different problem, delta H of fusion, and account for all of that energy as well before you actually have, let's say, 100 degrees Celsius water vapor. And then also, you could also have calculated then what would it take to get that same pot of 50 degrees Celsius water up to 200 degrees Celsius water vapor. You could again have a Q equals MC delta T to figure that out. So there's multiple steps sometimes now in determining some of those transitions. So we have some examples like that coming up here on the next slide. So this is kind of what I was referring to. You may want to review the calculation of the heat exchange between system and surroundings for temperature changes and phase changes. So temperature changes, that's the Q equals MC delta T, or MCS delta T, or MS delta T, depending on what you were calling specific heat. And for water, that was 4.184 joules per gram times degrees Celsius. And then again, we have to be careful about systems and surroundings in terms of you can have a change in temperature that's positive or negative, so on and so forth. So we just have to be a little bit careful with some stuff like that. So let's take a look at this first one. Calculate the amount of heat deposited on the skin of a person burned by 1 gram of liquid water at 100 degrees Celsius, and assume the body temperature is 37 degrees Celsius. So this is the setup for something like that. Q equals MC delta T. We have 1 gram of water. We have the specific heat of water is 4.184 joules per gram times degrees Celsius. And we have a change in temperature that water is going to transition, right? The T final is 37 degrees Celsius. T initial is 100 degrees Celsius. So that's dealing with the total temperature change and the energy that water can impart to the skin. So here's that whole setup. You can see we get negative 0.264 kilojoules. So again, it's negative based on what you're calling the system and the surroundings. Your skin being the surroundings, that water is losing 0.264 kilojoules. It is being gained by your skin, right? That's what would be going on there. Okay. So we could also add a second portion to this and calculate the amount of heat deposited by 1 gram of steam at 100 degrees Celsius. So let's say that water was not, it wasn't just liquid water at 100 degrees Celsius. Let's say it was steam at 100 degrees Celsius. Let's see how much heat would be deposited if that were the case. So here we need delta H vaporization, which we would look up on a table. It was on one of the prior slides table. So that was 40.79 kilojoules per mole. Again, this was negative. This condenses here versus vaporizing. So you're losing energy in this because that you're going from steam to liquid, as opposed to adding energy where you're going from liquid to vapor to steam. And then N, remember this is kilojoules per mole. So we need to get moles of water. So we're familiar with that. So 0.0555 moles of water. We just multiply those together to have moles cancel, and we'll get kilojoules. So here we get negative 2.26 kilojoules of energy that would be deposited just from that phase transition from steam to water at 100 degrees Celsius. So when we think about the total energy that's deposited onto your skin, we kind of have both of these. This is the prior problem, right? Was the water going from 100 degrees Celsius to 37 degrees Celsius. And this is just from the steam at 100 degrees Celsius transitioning to water at 100 degrees Celsius. So the total energy that's deposited then is negative 2.53 kilojoules. So most of that is actually coming from the steam transitioning to water at 100 degrees Celsius, not from the water at 100 degrees Celsius going to 37 degrees Celsius. So 100 degrees Celsius steam, we have this Q1, which is right here, to 100 degrees Celsius water, liquid, and then this Q2, which was from the prior problem. So you can see this is essentially justification for why steam is more dangerous than liquid water. Maybe it's less dangerous because you encounter it less, but that's why some steam burns can be particularly gruesome in comparison to even some fairly major hot water burns. So let's try one more of these. We'll kind of again do a two-part thing. So calculate the amount of energy necessary to warm 100 grams of water from 0 degrees Celsius to body temperature Again, assume the body temperature is 37 degrees. This is what this looks like. So 15.5 kilojoules. Again, we're going the opposite direction, so this ends up being positive. You can pause and take a look at that. And then we'll do a second set here. Calculate the amount of energy required to melt 100 grams of ice at 0 degrees Celsius, and then warm it to body temperature. So now again, we're going through that phase transition. So this is going to include both of those. So we have, instead now we have delta H fusion. We have 100 grams of water, so 5.55 moles of water. Again, this is a positive value, 6.01 kilojoules per mole. So we get 33.4 kilojoules per mole in that transition of ice just for the 100 grams of ice turning into 100 grams of water, all at 0 degrees Celsius. Okay, so that's what this is. 100 grams of ice at 0 degrees Celsius undergoing Q1, this being Q1, to 100 grams of water that's liquid. So this is the phase transition. And then we have our normal Q equals MC delta T, which is what I just had shown with 15.5. So the total energy here, 48.9 kilojoules, partly due to the phase change, partly due to the temperature change once it was liquid water. So this is what these can look like here. We often, I think, probably did not realize that it required so much energy to do these phase changes. We are familiar with, as you add heat, energy, that you change a temperature. But again, there are times where that's not true. Some of that energy can be imparted to changing a phase, not simply changing the temperature. So this is kind of a new idea here, probably.